Good evening, everyone. I'm Nilmoni, a research scholar at IIT Kharagpur. So I'm the TA for this course, Fourier Analysis and its applications. And this is the eighth live interaction session. Uh, and today we will see uh, whatever we have done in last week. And also, we will solve some problem analogous to your assignment problem. Okay, and yeah, first we will uh, see functional some tools from functional analysis which will be used in Fourier analysis. Okay, let us see. So first start with what is nonlinear space. Um, So a nonlinear space, very well. So nonlinear space is a vector space V and Android with a map. So this is a P and Android with this map. The map is basically, here V is a vector space, and this is a map from V to R or C. Okay, and basically this is called nonlinear space. This pair is called nonlinear space, and this is called norm. Okay, is called norm if all the following properties are satisfied. Okay, so one is norms, this norm, this should be positive, so non-negative. Okay, for all v in V, and second is norm v equals to 0 if and only v equals to 0. And third is triangle inequality hold. So v plus w norm v plus norm w. Okay. For all vw belongs to v. And 4 is norm tv equals to mod t time norm v for v belongs to v and t belongs to r. Okay. Maybe sometime you can take the t can be actually complex number. Okay. And next we will see what is Banach space. Banach space, and yeah, so Banach space is basically complete nonlinear space. So, but we know this complete space like does make sense uh, with metric space, right? When the norm comes from metric, then it makes sense, right? So yeah, so basically, so you have a norm, you have a nonlinear space on uh, V. Okay, so and we can define a metric space with from this we can define a metric space with the metric dVw is nothing but norm V minus W. Okay, so if V is, sorry, yes, if V D is complete, then we say V is Banach space. Okay. Hmm. Okay. Now, the most interesting example of a Banach space is CAB with subnorm. Okay. And CAB is basically collection of all continuous function, uh, real or complex valued continuous function, which is defined on closed interval AB. So this is uh, closed interval AB to R or C such that F is continuous. So this is a Banach space. So I'm not going to prove it how it is Banach. Okay, so I can explain like what is subnorm. So this is basically sup x belongs to AB mod of x. Okay, and some other examples. So LP space, you know what is LP space? 1 less equals to P less equals to infinity. They all are Banach space. And L to R, this is also Banach space. And this is very important in the theory of Fourier transform. And 3, yeah, Cx if X is compact metric space. Okay, and this is also Banach space. And the set of all continuous function on the closed unit disk. So if we take D is basically Z belongs to C such that mod Z is equals to 1, then uh, the set is F D to C. Okay, and F is continuous on D and F is holomorphic in the interior. Okay, and with respect to subnorm. Yeah, basically, so this is with respect to your p norm, so respectively, like for 1 less equals to p less than infinity, we have usual norm, p norm, and for infinity, this is a sup norm. So not sup norm, so infinity norm, L infinity. Okay, so essentially, so bounded. Okay, and for L to R, norm 2. Okay, norm 2. The square integral. Okay, norm. And yeah, these are some examples of Banach space. And then we will discuss one interesting space. This is Bergman space. This is Bergman space. This is a special Hilbert space. Okay, and yeah, this comes from actually L2 space. So first of all, let uh, omega be connected domain. This is important in C. And then your A omega we denote the set of all holomorphic functions omega and your and then we define this A2 omega by A omega intersection L2 omega. Okay, this is right. This the set of all measurable functions where the square integral is integrable actually. Okay, and so this is called Bergman space. Okay, and one theorem shows this Bergman space is actually a Hilbert space. Since this is a subset of L2, so this is complete and this is a closed subspace. Okay, and this is a closed subspace. Uh, so one can prove this is closed subspace. So that's why this is complete, and hence this is a Hilbert space. Okay, this is Hilbert space. The proof can be in your lecture notes or in lecture video. Okay, using mean value property of holomorphic function, one can do the proof. Okay. Mm. Now, one interesting topics, interesting thing we can discuss the Bayer category theorem and Banach-Stein's theorem. So for that, first we define continuous linear map on Banach spaces. Okay, so this is simple. So like in linear algebra, so suppose x and y are Banach space. Then we are interested in studying the linear transformation t x to y that are continuous. Okay, So the following are equivalent, and what number one is T is continuous. This is equivalent sorry, this is equivalent to T is continuous at any point. So in general, T continuous, in particular T is continuous at 0. 3, there is a constant, and there exists a constant m greater than 0 such that norm t x less equals to m. So that means your t is bounded, right? And fourth is t is uniformly. So each are equivalent, okay? Each two, any two equivalent. So uniformly continuous. Okay. Now next we discuss the Bayer category theorem. This is one of the most important result in general topology on which the mm, entire thing of function analysis. Okay, so yeah, so basically we need a complete metric space for this. So theorem is suppose X is complete metric space such that X equals to n equals to 1 to infinity En, where each En is closed, okay, then at least one of the sets n must have non-empty interior. Okay, so this can be proved by contradiction method. Okay, and uh, so using the denseness, okay, open denseness property. Okay, so to see the proof, one can check lecture notes or lecture video, and also then we will see what is Banach-Steinhaus theorem. Banach-Steinhaus theorem. So yeah, for here we don't need this theorem in general. Okay, but we need this theorem in a special case. Okay, and so special cases we need this for a sequence of bounded linear maps Tn x to c. Okay, yeah. Again, we say that a sequence of continuous linear forms Tn as above is pointwise bounded if for each x belongs to x there is a constant mx such that yes, so n belongs to n Tnx is equals to mx. And we say that the sequence of continuous linear map continuous not continuous sequence of yeah sequence of continuous linear forms Tn is uniformly bounded if there is a constant m such that this sub n belongs to natural number mod Tnx is equals to m for all x for all norm x is equals to 1. And now we can state in one line this theorem is originally if a sequence of continuous linear map Tnx from C is pointwise bounded, then it is uniformly bounded. Okay, so what we have for this theorem. So basically, first we have seen like what is pointwise bounded. This is basically there. If for each x belongs to x, there is a constant mx. So it depends. This constant depends on x, and for uniformly bounded, this constant does not depend on x. Okay, and hold for all norm less equals to 1. Okay, and this Banach-Steiner theorem says if your a sequence of continuous linear map this is pointwise bounded, then it is automatically uniformly bounded. Okay. Yeah. Okay. Now we will discuss one interesting thing. One thing basically, this is existence of a continuous function whose Fourier series diverges at the origin. So here, so yeah, so we already seen that, have seen that this Banach-Stein's theorem, but where it is used in Fourier analysis. So Banach-Stein's theorem actually helps us to get the existence of a continuous function whose Fourier series diverges at the origin. Okay, so first we want to establish the set of all. Sorry, not yeah. We established that the set of all 2 pi periodic continuous function whose Fourier series at the origin diverges uh, and is a dense subset of all the sets of all 2 pi periodic. Okay. So for that, we can recall from past 2 3 lectures. Okay, not past 2 3 weeks actually. So yeah, so recall the nth partial sum. This is Sn f of x, f of t, tn x minus t dt. Sorry, and where this dn is Dirichlet kernel. So what we will show. So we will show this Sn f0. Sn f0, this is equals to your, okay, let us will show this fails to converge as n tending to infinity for a large collection of function f, which is from this set denotes a set of all periodic 2 pi periodic function. Okay, and yeah, so for that, let Snf comma 0, this is Tnf. Like write this only. For simplicity, we are like, so this is obviously a function of ape, right? So Snf, so we can ignore this 0. Okay, so, so we can write like this only, and Tnf, sorry, where Tnf is minus pi to pi ft dnt dt. So again, one can show this by contradiction. Okay, okay. So yeah, uh, if possible, let all the Fourier series of every function in minus pi to pi converges at the so this is this actually we are going to prove the existence, right? So if we like contradict this statement, then we can say there exists a function from this uh, which diverges at the origin. Okay, and at the origin. Okay, so we will see it by contradiction. Okay, and so what our assumption says that basically S and F comma 0, this is T same as T and F, and this converges as n tending to infinity. And okay, so since this is converges, so we can say, right, this sequence of function is bounded for each F belongs to periodic minus pi to pi, and since this is bounded means so for each F this is bounded, so this is pointwise bounded. So by Banach-Stein's theorem, mm, this is uniformly bounded, so that we can write there must be one constant m greater than 0 such that so does not depend on F. Okay, does not depend on X, sorry, F here, F, such that mm, for all okay. And yeah, so see, so already we have seen this SNF is your minus pi to pi ft tn x comma t, right? Sorry, x minus t. So this gives you minus pi to pi ft dnt. So dn minus t equals to dnt. This is even function, no problem at all. This equals to m for all n belongs to natural number, and for all f belongs to minus pi to pi with minus 1 less equals to f less equals to 1. Okay, now one thing, we restrict ourselves. Okay, we restrict f as a real valued function only. We restrict f as real valued function. Okay, And yeah, also we have seen before minus pi to pi mod tnt dt. This is c log n. Okay, so write it 1 and is 2. Okay, okay. Now it is time to put something special function as fx. So if we take fx as signum function denoted denoted by sigma t, which takes the value 1 and minus 1 if on the subintervals where this t and t is positive, and uh, minus 1 on those subinterval where d and t is negative. So and this says basically you from 7, sorry, from 1, so you will get so we are taking fx as signum function and minus pi to pi mod dnt dt less equals to m for all n belongs to natural number. And see, this contradicts this, right? This is not bounded at all. Okay, the growth is log n. Okay, as n tending to infinity, so this is not bounded. So which contradict 2? Which contradict 2? Okay, so our assumption is wrong, and but the only objection is that to this reasoning is that the function that takes only values plus minus 1, which is not continuous. So observe that the sign of dnt alternates in the alternate interval of length pi by n, so that the signum function we have chosen alternate between minus 1 to 1 successively intervals of length pi by n. And such lies in L1 minus pi to pi. Okay, so we did not take f as a f continuous function, right? So the assumption wrong. So now uh, if we see what about the existence of continuous function, okay, then we can use Lusin's theorem uh, to and obtain our signum function sigma as a limit of sequence fj of continuous function. And yeah, so see, the sigma is your not continuous, right? But so we can approximate this as a continuous function and sequence of continuous function, so by Lusin theorem. Okay, with L1 norm and minus pi to pi mod fj t minus sigma t dt goes to 0 as j tending to infinity. So in that case we can bound maybe and minus pi to pi mod tnt dt equals to minus pi to pi dnt sigma dt, and this is equals to minus pi to pi dnt sigma t minus fgt dt plus minus pi to pi dnt fgt dt, and this is less equals to minus pi to pi mod dnt mod sigma t minus fgt dt plus minus pi to pi dnt fgt, sorry, dt mod. Okay, and this is less equals to something, um yeah, so dnt is the integration of dnt is login, and this is roughly we can like bound by capital N, and this minus pi to pi, and yeah, mod sigma t minus fgt dt, and this is bounded, right? So dnt time, so here mod is not there, so that's why we can bound this. Okay, and so now, but here for fixed n, for fixed n and j tending to infinity, so minus pi to pi mod dnt dt, this is less equals to m. Okay, for fixed m, and which is contradiction, which is contradiction, because this is a arbitrary large but this is constant. So yeah, this is how we can construct a continuous function. Okay, so that whose Fourier series is divergent at the origin. Okay, now now one thing we need to establish the following thing. So this ln minus pi to pi, already assume it. This is c time log n. Okay, this ln is called basically Lebesgue constants. Okay, now behavior of the Lebesgue constants. Okay, so now it is it is sufficient to look at only 0 to pi interval. So we know dnt is sin n plus half t divided by sin t by 2. Okay, and this changes sign at points k pi divided by n plus half. Okay, so k equals to 0, 1, 2, and so on. and which divide the interval 0 to pi into finitely many subintervals, each of length pi by n plus half. And also one can uh, see this 1 by sine t by 2 greater equals to 1 by t by 2, that is 2 by t. Okay, so we have dnt mod, this is 2 by t mod sine n plus half t. Okay, and on the smaller subinterval of length pi by 2 times n plus 2, uh, so ik equals to t, so that pi k plus 1 by 4 n plus half less equals to t less equals to pi k plus 3 by 4 n plus half. Okay, and we have the estimates sine t n plus half greater equals to 1 by root 2. And now the mod t and t, this is greater equals to 1 by t, and this is greater equals to the interval 1 by t, so 2 by pi 2n plus 1 4 k plus 3 on ik, of course, and integrating ik tn t dt 2 by 4k plus 3, and okay, so just multiply the length of ik, and but that should be your 1 by 2n plus 1 times pi by 2n plus 1, pi by 2n plus 1, the interval we have taken. Okay, and then finally if we add all the interval, this is c time 1 plus half plus dot dot plus 1 by n, and this is some constant time log n, and this is what we have wanted to prove. Okay, okay, now we will see some different things. So Hilbert space basis. Okay, something about Hamel basis. Okay, but what is Hilbert space first? Okay, so what is Hilbert space? So consider H. Hilbert space. So H is a vector space endowed with an inner product such that dv such that the this metric defined by this inner product, instead of this you can write like this. Okay. And this is complete. This should be complete. This matrix space. Now the norm of a vector V here we can define like this. Hmm. Okay. And yeah, so we have seen in chapter 2 actually, in chapter 2 and on or week 2. Okay, some properties of inner product space, such as Pythagorean theorem, parallelogram identity, and which gives you some idea to study Hilbert space. And okay, so this V and W in H are said to be perpendicular or orthogonal, denoted by VW, and if VW is 0. Okay, and the ortho complement of the vector subspace. Okay, so this is V, and this is a ortho complement of V. X belongs to H such that X V for all V belongs to V. And yeah, now we check basis and Hamel basis. Okay, so in for finite dimensional case, we already know from uh, linear algebra. Okay, so this is called actually Hamel basis. Okay, but in general, for any dimension, we call for any dimensional space, Hilbert space or vector space, so we call basis. Okay, so a basis, a basis in a Hilbert space is a linearly independent subset B of H such that the closure of span of B is the whole of H. So that is if such that closure span B is closure is H. Okay, a Hilbert space uh, cannot have a countable Hamel basis unless it is finite dimensional. Okay, and this is from Bayer category theorem. Okay, Okay, so let us prove this. This is okay. Let us call it theorem. Okay, so suppose the Hamel basis is countable. Okay, so a finite dimensional subspace of a Hilbert space is always closed and has empty interior. If your Hilbert space H is in finite dimension. Okay, so Hamel basis, suppose Hamel basis is countable, so Hamel basis like this V1, V2 and so on. Okay, and they can be look at linear span of V1 dot Vn. So which is finite dimensional and closed and so empty interior. Okay, and so this union n equals to 1 to infinity En, this is basically H because the Hamel basis is this. Okay, and yeah, and then Bayer category Bayer category theorem says one of En has non-empty interior, which is contradiction. Already we have checked, right? They always closed, and that's why empty interior. Everything has empty interior. All in. Okay. Let us give some example of basis. Okay. The classical example of Hilbert space is, you know, L to AB. So LP is complete. So P equals to 2 if and only LP is Hilbert. Okay, already we have seen Hilbert space. Okay, and so we consider here equals to minus pi, b equals to pi. Then we already have seen the partial sum of the Fourier series of f belongs to L minus pi to pi L2. So this partial sum of Fourier series of f converges in L2 norm to f. Okay. Uh, yes. Because of the partial sum of Fourier series are a finite linear combination of, this is as usual. Okay, partial sum sums of the Fourier series are finite linear combination of 1 cos x sin x cos 2x sin 2x and so on. And so we infer that linear span of this is dense in this linear span of this is dense in L2 minus pi to pi. And so this is an orthogonal basis. One can, of course, normalize this and obtain a countable orthonormal basis. Okay. And next is the function. Hermite function. Hermite function. A Hermite polynomial are solution of Hermite differential equation. Differential equation this y dash plus 2 lambda y equals to 0, and solution is like power series n equals to 0 to infinity a n x to the power n, and so that 0 to infinity x to the power n n plus 2 n plus 2 n plus 1 minus okay, no, we are not discussing this actually. Okay, so we can write a solution like this. Okay, something a naught of this plus a1 times this. So using power series solution. Okay, and so what? So how looks like the Hermite polynomial? Okay, so that is important. So explicit formula for Hermite polynomial, Hermite function. This is basically qnx e to the power x squared dn e to the power minus x squared. Okay. So one can check orthogonality and normalizing the Hermite polynomial, and In last, one can check the completeness of Hermit function because this also like a example of Hilbert space. Okay. Okay. So today, up to this, uh, we recall whatever we have done last week. Now we can do some problems. Okay, and related to your assignment, last assignment. Okay, so first question is consider the Bergman space A to D. So the absolute value of the Fourier coefficient Jy comma Z cube. Okay, so what is J1Z? This is a Bessel function, right? You know what is J1Z. Gamma k plus 2 and Z by 2, 2k plus 1. This is J1Z. Now calculate J1Z comma Z cube. Put this equals to 0 to infinity minus 1 to the power k factorial gamma k plus 2 j by 2 2k plus 1 sorry z cube, and this is equals to, so you can take some outside, uh, k factorial, and this is k plus 1 factorial, and z by 2 to the power 2k plus 1. So the orthogonality condition gives you basically this gives you some value, some non-zero value when k equals to your the power should be matched k equals to 1. Okay, so this is what you will get: minus 1 1 factorial 2 factorial and z cube, and this is minus 1 by 2. Sorry, not z, so z by 2, this is 1 by 2 to the power 3, so 1 by 8 will come outside, 1 by 8, and this z cube, and this is the norm, uh, so norm square. So here norm comes from Bergman space, so this is basically 1 by 16 norm z square. Okay, so in Bachmann space A to D. So your norm A to D square is D mod fz square dA. Okay, so here your fz is z cube. So one can write like this is like this 0 to 1, 0 to 2 pi. First write 0 to 2 pi, 0 to 1 r dr d theta. Okay, and also one thing one we could write we here f of r comma theta modulus square dr d theta. Okay, so here uh, your z cube is there, so z equals to r times e to the power I theta. So mod z cube mod equals to, so this is r cube. So and 0 to 2 pi, 0 to 1. So write like here. Uh, okay. Uh, J1 z comma z cube, right? This is minus 1 by 16, 0 to 2 pi, 0 to 1, and so r cube square, and also here I made a mistake. This should be r dr d theta, r dr d theta. So minus 16, 2 pi. So this is 0 to 1 r to the power 7 dr. So minus 1 by 16, 2 pi. So 1 by 8. So 8. So this is minus pi by 64. And the absolute value of this is this modulus minus pi by 64. This is pi by 64. Okay. Well, I hope it is clear to everyone. And the next question. The value of sin z square in L to D, where D is the unit disk. Okay, solution. So you know, right? Sin z is your equal to 0 to infinity minus 1 to the power n, 2n plus 1 factorial, z to the power 2n plus 1. Okay, so in L2 D, so the norm f square is simple 0 to 2 pi, 0 to 1. Of course, on unit disk. Okay. 0 to 1. F of r comma theta square r dr d theta. So find it, right? So this sum n equal to 0 to infinity minus 1 to the power n to n plus 1 factorial to n plus 1. Same right here. This is equal to 0 to infinity minus 1 to the power n by. So when it will give some value when this and this are same, like the powers would be matched. Okay, otherwise from orthogonality condition this will give 0. So that's why minus n to n plus 1 factorial will go outside and z to n plus 1 z to n plus 1. Okay, and this is you will, from this you will get 1 by 2n plus 1 factorial 1 by 2n plus 1 factorial, and this is from here 0 to 2 pi, and so z equals to here r e to the power I theta. So the modulus will come, right? So mod z is basically r. So r to the power 2n plus 1 into r dr d theta. Okay, so this sum n equals to 0 to infinity 1 by 2n plus 1 0 to 1 also. So 2n factorial 2n plus 1 factorial 2 pi r to the power 2n plus 2 2n plus 2 factorial, sorry not factorial, 2n plus 2 only 0 to 1, and then this will give you 2n plus 1 factorial, and this you multiply 2n plus 2 with this 2n plus 2 factorial, and 2 pi is outside. Okay, this is the value of your this norm sin z square on with respect to norm of L2 norm actually, yeah, on the unit disk. Okay, so I hope it is clear to everyone. And next question, which of the following is a Herbert polynomial? So ddx. So first one is exponential x square by 2 minus x square by 2 x square, right? So this is just from definition. Already we have seen the option is C is true. So this is the some constant time. This is only the Hermite polynomial. Remaining ones are not correct. Okay, one can check by orthogonality conditions, and these are not correct. Okay. Okay, so question 4. Which of the following are true? has a countable Hamel basis set of polynomials has a countable Hamel basis. The Parkman space A to D has an countable Hamel basis. The space L201 has an uncountable Hamel basis. Okay, how to solve it? So we already have seen, right? This is correct. So you can consider 1x squared dot dot dot. This is a countable Hamel basis. Okay. Your span is 1x 2x to the power n, and this is also true with same reason, and but this is not true because the Barksman space has an infinite sorry uncountable Hamel basis, because this is already we have seen. Okay, so this Barksman space is Hilbert space, and yeah, the cardinality of Hamel basis is uncountable if any infinite dimensional Hilbert space has infinite dimension. Sorry, not true. Sorry, if any infinite dimensional Hilbert space. In any infinite dimension, so this is infinite dimensional Hilbert space. So it should have an uncountable Hamel basis. So that's why it is not correct. And next, by the same reason, this has an uncountable Hamel basis. Okay, so this is also correct. Okay, I hope it is clear. Okay, so today up to this, we just mm, we have like learned your some function analysis tools, and then we used this in Fourier analysis, and something about Hilbert space, Hamel basis, and then Hermite polynomials. Okay, so next day we will discuss more on Hermite polynomials. Okay, some orthogonality condition of Hermite polynomial, normalizing, and completeness of Hermite polynomials. Okay, and some other special function that comes from solution of differential equation. And at the end, we will see some Chebyshev polynomials. Okay. Okay. So today I stop here, and next week at the same time we will meet. Okay. Thank you.